Okay, so last time we had a little discussion about, we finished off with defining how we calculate errors, etc. And we start talking about the different types of errors, the modeling errors, human errors, programming errors, etc. And said we're going to focus in this class on errors related only to numerical methods. And those were roundoff, truncation, and iteration errors. Okay. For roundoff errors, we kind of beat them up quite a bit, discussing them because they're so important. In fact, on your second homework assignment, which is assigned today, due next Thursday, you're going to solve the problem of what happened with the Patriot missile. You'll see the explanation in the assignment and how to kind of do the calculation to estimate and understand why the missile system failed to intercept the Scud. And we left off with round-off errors. And today we're going to finish off with truncation iteration, and we'll start on our next chapter. I'd like to have your name tags put on the table and group names, please. If you haven't thought of a group name yet, please think of one right now, because we're going to start employing that methodology as we move on. Okay. Now, truncation error was the second type of error that we talked about last time. And we defined the truncation error simply as the error committed when you take an exact mathematical expression and truncate it. The classic example of that is the Taylor series. And we did that on Tuesday, where the Taylor series was given as an infinite summation, right? The exponential, the sine, the cosine, the logarithm, all of those functions are given as an infinite summation of terms, okay, to compute the cosine of x or the exponential of x. However, in practice, we can't do an infinite summation. So we choose a fixed number of terms based maybe on a tolerance, like we did in the exercise in class, right? Or based on a fixed number of terms. Whatever is left from that truncation is the truncation error, okay? So the truncated Taylor series we presented earlier was an example of that. Now, notice that you might hear the word truncation error refer to chopping a number. So what we have called round-off error. So some folks in computer science call truncation error when they're dealing with numbers. They call truncation error as the error committed when they take a number and truncate it, okay? To be clear, in this class, truncation error refers to taking an exact mathematical expression and truncating it, okay? No ambiguity. The final type of error, which is just generally kind of a little bit elusive, even to me, sometimes I'm like, it's hard to just put your finger on it until you start dealing with iterative solvers, which is going to be the topic for the next few weeks of this class. But in many cases, and specifically in iterative solvers, but there are some other numerical recipes where you would start with a guess of the true solution or of the answer. And then you have a recipe. And by recipe, I mean, you take that guess, you multiply it by 2, divide it by 4, do something, et cetera, and then you improve on that guess. Then you take that improved guess and put it again through that recipe and keep repeating until you hopefully converge to the true answer, okay? The distance between that guess and the subsequent improved guesses and the true solution, that's called iteration error. Okay, so you might take a method that uses iteration and start with two different initial guesses. They will both converge to the right answer, but your iteration error will be different because you're starting from different initial guesses, right? You're starting from different initial guesses. So that error between the current iteration and the final answer, we define that loosely as the iteration error, okay? So that's generally, like I said, strictly encountered in iterative methods, okay? to refine a guess. Now, one example I kind of give of this, and I inherited that from Professor Sutherland, which I think is a cool example. Take a dictionary that has 500 pages on it, okay? And you ask the question, kind of, where do you think the word muse, on what page is the word muse located at, okay? And one hint is that the letter M is kind of halfway through the alphabet, okay? So you might say, okay, because the letter M is kind of in the middle, and I'm going to assume that half the words start, half the letters cover half the words in the dictionary, and the other half covers the other half. A good guess might be page 250. Let's say the true answer is that the word muse is on page 193. So the difference between 250 and 193, that's your initial iteration error. So you open page 250, and they're like, oh, there's no word muse over there, but, there's the letter N. So you know what? Maybe I'm kind of a little bit before. I gotta move backwards. So what you do then? You take, again, you go to page 125, so you cut it in half, right? And then you keep cutting in half until you reach the answer. So here's kind of one algorithm for that, and that's called the bisection method. There's no reason behind it. You could have cut the pages by 1/3, okay? You could have said, I'm going to start at 350 or 333, and then decide if I'm to the left or to the right, and then cut that number in half, and then or third, or then keep cutting it in third until you get to, and you're going to converge. That method is a converging method. You're going to get to the answer. Now, the distance between your current page that you've improved or you're guessing and the true page, that's your iteration error. That's the best description I have of iteration error. Okay. And with that, we finish that chapter on errors. And we will start our next chapter on linear solvers. Okay. So if I can find that, let me open linear solvers. Okay. This, I don't know, it sounded like that, but this chapter is, sorry about that. So this chapter is by far one of the potentially perceived as the most challenging, because there's a lot of ground to cover. There's a lot of ideas that we need to absorb, and there's a lot of programming. Okay, so that's kind of like, if you plot the, on the x-axis, you plot, chapters in this course, and on the y-axis, you plot difficulty. We started kind of easy, and now we're going to go really up, and then it slows down a little bit. And then by the time we hit nonlinear solvers and ODE is going to get a little bit more challenging again. So, this is the first storm in this semester. I'm not saying this to scare you. I think you're a tough bunch based on what I've seen so far and compared to previous years. So, I think you will all rise up to the challenge. And so I want to make this fun as well. Okay. Let me make sure that my screen sharing has audio in it, because I want to motivate you with a video. Okay, I'm going to stop the share for a moment. Go back on Zoom. Share sound. Okay. All right. Can you guys hear me on Zoom? I can't see you. If someone can just give me thumbs up in the chat.
We can hear you.
Can you still hear me?
We can hear you.
Sorry, one moment. I do not think they can hear me on Zoom. Can you hear me on Zoom? Okay.
Yes.
Perfect. Yes. Thought I lost you for a moment. Okay. So I'm going to start with a motivating example. And again, I don't want to be the speaker of doom, but like all of these examples are disasters, unfortunately. But there's this thing in cognitive science that, the way we process ideas in our mind, an idea is more likely, there's different levels of storage in your brain. I am looking for deep storage to kind of plant ideas deeply in your brain so that they're there whenever you need to access them. There's deep storage, and then there's retrieval. With retrieval, that's what you do with your homework assignments and kind of questions and activities. So, but to access a deep storage, in your brain, you have to evoke emotion. Okay, so an idea is more likely to stick in your brain is if it makes you feel like so concerned about something or makes you very excited and happy, right? And so, but it just so happens that these examples I'm picking, they are unfortunately correlated with, unfortunate events, but they will have the same effect. Those events happened in reality, but they have the same effect of them hopefully sticking in your brain. So this example, so in the chapter on errors, we saw the example of the round of error. This one is an example of linear systems of equations and the need for linear solvers. Although it's not directly apparent, they never mention the word linear solvers, but I know that they use linear solvers because my colleague did the simulation at the National Institute of Standards and Technology. Randy McDermott, he was actually a PhD student here at the University of Utah. And so he is behind the software called the Fire Dynamics Simulator. That is the standard software that is used worldwide to investigate fire accidents. And it's tremendous work that they're doing at NIST. So I'll share this with you. It's about a 10-minute video, but I'll probably chop it halfway, stop it at 5 minutes. But I encourage you to watch it, and then I'll explain what's happening behind the scenes. Okay, so let's see. Oops.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in 2 line-of-duty deaths. On June 2, 2011, a fire in a multi-level residential structure claimed the life of a lieutenant and firefighter paramedic from Engine 26 of the San Francisco Fire Department. NIST examined the fire dynamics of this incident at the request and the San Francisco Fire Department.
On Zoom.
At 10:45 in the morning, a call was dispatched for a reported fire due to an electrical short. Engine 26 arrived on scene within 3 minutes of the dispatch and reported light smoke conditions. They made entry through the front door with 1 3/4-inch hose line. At approximately 10:54,
sorry, let me go back.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight.
Let me try something. I'm going to try to pipe my audio into the speaker system in the room. Let's see. Those on Zoom, you can watch on your internet browser.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in 2 line-of-duty deaths. On June 2, 2011, A fire in a multi-level residential structure claimed the life of a lieutenant and firefighter paramedic
So
from Engine
this fire in a
26
residential
of the San
structure in
Francisco
San
Fire
Francisco,
Department.
California, claimed the lives of
NIST examined
two
the fire
firefighters, a
dynamics of this
lieutenant and a
incident at the
firefighter.
request of NIOSH
And
and the San Francisco Fire Department.
essentially what
At
happened,
10:45 in the morning,
they
a call was
miscommunicated with each
dispatched for a
other,
reported fire due
and
to an electrical
they
short.
opened,
Engine
so
26
suppose there's a
arrived on
fire here
scene
in
within
this
3
room.
minutes of the dispatch
Don't open two
and reported
doors.
light
You're
smoke
gonna bring in more
conditions.
oxygen.
They
You're
made
gonna
entry through
put
the front door
everyone,
with 1
downstream
3/4
of
inch
the
hose
fire
line.
in the
At
line
approximately
of danger.
10:54, about 6
And,
minutes
you know,
after
they
the
didn't know what
arrival of
happened
Engine
then, but the
26,
CFD
Battalion Chief 9
simulations
followed the Engine
ended up
26 hose
showing what
line up the
happened.
front
So
stairs,
I'm
into the
sorry
front
that
door,
you
and
can't
then
figure
down the
out a way
stairs to the
to
first
get this
floor
audio
or
to
street
work
level
over
of the
here.
house.
This huge advanced system.
Battalion Chief 9 had a
Unfortunately,
face-to-face discussion
I
with the
will
victims.
encourage you to watch it at
During
home,
this
if you
discussion,
don't mind.
Engine 26
But the
confirms
idea
that
is
the
that,
fire is below them, and
you know, they
Battalion Chief
went and
9
they
indicates that
did
the attack will be made from the basement level
after
on the
the
B side.
investigation of what happened, they
The battalion
ran
chief exited the building.
calculations of how the fire might
Engine
have
26
spread
remained in
and what
position near the top of the
caused,
stairway leading
the
into the
unfortunate
basement.
deaths of
This was the
these
last
great
communication
firefighters.
with the Engine 26
And the
crew
CFD
members
simulations
inside of the
ended up
structure.
showing that because one
Within
of the doors
11
was
minutes
opened
of
in the
Engine
basement,
26's arrival on
and
the
the
scene,
firefighters were
the
gonna,
large windows
imagine
that
there's
made
a
up
fire over
most
here,
of the
smoke
side
is
seawall of the
kinda
basement
moving.
level
You have
began
one
to
door open
fail
over
due to
there.
heat
There's
from the
oxygen
fire.
coming in and smoke
As the
kinda
windows
leaving,
broke,
and a bunch
fresh
of
air
firefighters
mixed
are
with
standing
hot
over here.
fuel-rich
You open
gases
the
in the
other door,
basement,
you
which
create
increased the
a
heat
fresh
release rate of
supply
the fire.
oxygen coming down from over
The
there,
increase in
and it
heat
moved the
release rate
fire
resulted in
directly
the
in the
rapid
direction
failure of the 6
firefighters.
window
They
panels.
were
It took
exposed to
less than
very
2
high levels of
minutes
heat,
for all of the
unfortunately.
windows to fail.
And they lost their lives because of that.
After the
That's
rear
like if you
basement
ask me if you
windows
know a
began to
firefighter. My neighbor
self-vent,
is a firefighter.
Engine 24 and
And
Rescue
you
1A
ask them
tried
about
to
this,
make
they're like,
entry
"Don't
through the
open any doors.
pedestrian
You
door in
gotta,"
the garage
like,
to attack
they
the
have to
fire,
plan and
but they were
communicate
forced
correctly
back by
about it, but,
extreme heat and
unfortunately,
heavy black smoke.
in that incident,
With
they
the
did not
pedestrian
communicate
door
properly.
between
And
the
so,
garage and the first floor hallway
the
open,
investigation
heavy black
showed
smoke
that,
began flowing out of the open.
the simulation. So the point is that I want to show you here is that they ran CFD calculations. So these are computational
Fire
fluid
gas
dynamics
the center of the
calculations.
stairway from the basement shows the pressure plane along the center
Showing
of the
how-
stairway
so
from the
they ended
basement
up
to the laundry
opening
room
this
landing between the basement and the first floor. An
So I
estimate
think,
of the
yes, this
pressure
basement
increase
window
is shown
failed,
before
then
and after the first
firefighters were
basement
over
window
here,
failed.
and it ended up pushing all the
One of the
fire in
hazards
that-
to
in that
firefighters
direction.
located in
Okay.
the exhaust portion of the flow path is convective heat transfer.
So this explains the whole thing. The video explains the whole thing.
And are
But
flowing
this
up the
method, where you're seeing these
well,
kind of
then splitting on the
colors
first
and
floor,
animations,
with
et
some
cetera,
of the flow
these are
continuing up
actual
another
fluid
stairwell to the
dynamics
open front door,
calculations, okay? And this
and the
is
rest of the hot
my
gas flow
active
moving
area of
out of the
research,
open
and,
pedestrian doorway through the garage.
You know, NIST and
Notice
my
that
group,
the
we've
open
collaborated
basement
in the
windows
past
on the
and
rear of the
talked
house
about
serve as
improving,
bidirectional
simulation methods,
vents,
et cetera, but
with fire
all of
gases
these
exiting the
simulation
upper
methods,
portions and
they
air entering the
result
lower
in a
portions.
system of
While on the
linear
front side of the
equations
house,
that you have to
the
solve.
front door and the door to the
so
garage are
my
unidirectional
idea here
vents,
is that
serving only
this
as
is a
an exhaust
motivating
for the
example
fire
that linear
gases.
system of equations, you know,
There have been many
they're
previous
actual, they're
fire
realistic,
incidents
they're
in which
important,
changes
they
in the
can be
flow
used,
paths have had an adverse
to
impact on
understand and solve
firefighter and
complex
occupant safety.
mysteries and,
Fires
help us
with
improve
rapidly
our
developing or
response in
changing flow
firefighting, for
paths
example.
are a significant hazard to
I advise
firefighters.
you to watch the video
The development
at
of
home, where you can actually hear what the person is saying. I apologize about this. Oh, man. Okay, so I'm gonna get back to the to the slides. So the idea is that using computational fluid dynamics, we solve fluid and heat transfer equations, and the numerical solution of that, and you will see in a tangible example of how we start with a fluid or a heat transfer problem, and that leads us to a system of equations. By the end of the semester, you will be doing that. You will learn how to do that. In this chapter, we're going to solve a heat transfer problem in a piece of material, and we'll show you how to solve that problem numerically. You have to solve a system of linear equations, okay? But to get there, we have to get a few things out of the way, okay? I like learning objectives. So each chapter has a bunch of learning objectives. This is a non-exhaustive list. of the things you're going to learn. So this is a subset of what you will probably be learning in this chapter. You'll be able to define a linear equation, distinguish between a linear and nonlinear equations, identify a linear system of equations. It's kind of boring to just read from the slides, but kind of helps remind us of what we're going to learn. You'll be able to write a linear system of equations in matrix form. So from after this chapter, you're going to come out thinking every time you see a matrix, you're going to think of the matrix as, oh, matrix is nothing more than a fancy representation of a system of linear equations. That's all there is to a matrix, okay? A fancy representation of a system of linear equations, okay? Identify rows and columns in a matrix, identify some common types of matrices we deal with, dense, triangular, diagonal, sparse, tridiagonal, etc. Define what we mean by a sparse matrix, define the objectives of a linear solver. Why do we need a linear solver, okay? And define the two approaches or the two types of linear solvers, which are direct and iterative. Classify a linear system of equations and identify which methodology is better. So I give you a matrix, and then you say, okay, this matrix corresponds to a system of equations, but with this matrix, which method is better, direct or iterative? You'll be able to tell that. Use the TDMA, which is the tridiagonal matrix algorithm, which is a direct solution method to solve a tridiagonal system of equations. Those systems arise from heat transfer and fluid mechanics problems, okay? There's pentadiagonal, and there's even higher diagonal systems. So, those show up all the time in our work, in actual engineering and engineering science work. So these are very handy tools you're going to be learning. You will learn to do this by hand and using Python. You'll be able to build tridiagonal matrices in Python, write Python code to do the tridiagonal matrix algorithm, use Python code to solve for the temperature distribution in a one-dimensional piece of material. We can't do 2D right now. We need a little bit more work to get there. And identify when a system is not, what diagonal dominance is, and when it's not diagonally dominant, how to make it diagonally dominant. You'll see what that means. The idea behind iterative methods, and then finally write code for 3 iterative methods: Jacobi, Gauss, Seidel, and successive over relaxation. Okay, let's start. What is a linear equation? Okay, I'll give you the answer. A linear equation is simply an equation where the unknowns, the things that you are looking to find an answer for, okay, show up in a linear fashion. So in other words, they're not squared, they're not under a complex function like cosine, exponential, okay? So these are examples of linear equations where the unknown here is x, unknown is y, unknown is u. And nonlinear equations where unknown is x, this is x squared, so this is a nonlinear equation, a nonlinear equation, and nonlinear equation. Okay, so now let me ask you this. I have a marker on me, but suppose that we take this equation, ay equals c. The unknown is y, and a and c are parameters. What that means, they're input. They are brought in from measurements, from somewhere else. But this is the equation. In this equation, I'm solving for y. So what if you had a squared y equals square root of c? Is that still a linear equation? Yeah, why? Yeah. Then you can call a cubed, you can call it d, and square root of c, you can call it e. But y is the unknown you're looking for, right? Fundamentally, y is the unknown you're looking for, okay? Okay. Now, systems of linear equations are just that. You take a collection of linear equations with more than one unknown, so x, y, z, or x1, x2, x3, or t1, t2, t3, t4, t15, Each one of those has an equation where those unknowns show up linearly, okay? For example, 2x plus 3y plus 5 and 5x plus 3y plus 7. If you remember your math, these are 2 equations and 2 unknowns, so they are well defined. We have enough information to solve for x and y. You can solve this by hand, but that's a system of linear equations. You could have 2 billion equations like that. It's still a system of linear equations. Okay. Now, why do we need those? Because, as you're studying engineering, and in science and engineering, systems of linear equations are going to be everywhere. And especially if you end up doing computing, if you're doing anything, that has to do with data processing, numerical methods, optimization, discretization, you're going to end up with systems of linear equations. So it's going to make sense to study them before we do anything in numerical methods. You're going to see linear equations in interpolation. We're going to see linear equations when we're solving nonlinear systems of equations. We're going to see linear equations when we're solving ODEs. And if we get to PDEs, you'll see also linear systems of equations in PDEs. They're everywhere, literally. So that's why we start teaching linear equations. Okay. So now I'm going to take an example from separations and show you how you can derive a system of linear equations. Now, in this course, again, remember, I'm not holding you accountable to find the system, to derive the physics. Generally, I'll give you the system of equations and tell you what it describes. Sometimes I go on tangents to explain a little bit more in depth of where the equations came from. But, occasionally there are simple examples like this one where, with just basic logic, you are able to derive a system of equations, or you're able to derive something yourself. So this is an example in separations. Essentially, what separations do, they take a mixture of compounds. In this case, we're going to take 3 compounds, A, B, and C. They're coming in at a mass flow rate of 10 kilograms per second. And what these WA, WB, WC are, they are essentially the mass fractions of the incoming stream. So what this is saying is that 20% of these 10 kilograms per second correspond to compound A, 60% correspond to compound B, and 20% correspond to compound C. Okay? So 2 kilograms per second correspond to compound A, 6 kilograms per second correspond to compound B, and 2 kilograms per second correspond to compound C. So in other words, the mass flow rate of component I is simply the mass fraction of I times the total mass flow rate. Okay? Now, in this separation system, it just happens that we are able to know so this compound goes through a process over here, another process over there, and it tries to separate the compound separate. So our objective is to look at the station 1 up there. 93% of the outcome is compound B, and over here, there's like 75% C and 25%, 26% A, 74% C, and this is still a kind of crazy mixture, but we might be interested in just collecting compound B using this separation process. The point is, we can measure the percentages of these compounds at each of these locations. Your task is to find the mass flow rates at station 1, station 2, and station 3. Okay? We're going to try to do this together. Okay? First, I'll let you do it as a group. So I want you to develop just the equations for x1, x2, and x3. In other words, the flow rates at station 1, station 2, and station 3. I'll give you the first equation, right? Mass should be conserved, right? So whatever is coming in over here, the 10 kilograms per second, it's only going to go to x1, x2, and x3. So x1 plus x2 plus x3 is 10, right? That's your first equation. Now, think about your other equations, okay? You have 3 unknowns, so you need 3 equations. I gave you one of the equations, you need 2 more. Think about it. If you have the slides, the answer is on the next slide, but don't use that because you will not learn anything. This formula is very important, okay? This formula is very important. So think about what happens to the compound A, the flow rate of A that's coming in. How does it go? So what's the flow rate of A that's coming in? 0.2 times 10, right? So that's 2 kilograms per second. Where is that going to go? It's going to go to WA times X1 plus WA times X2 plus W, right? It's just mass conservation. Okay, good job. Yeah, you got it. Just find the equations, don't solve them.
We're keeping the same amount of A, B, and C.
Yes, yes, it's conserved. Yeah, it has to be. There's no reaction. It has to be conserved. Yeah, yep, exactly. Yes, thank you. Good point. I don't want to go into reactions and that kind of stuff, but yes, good point. Yes, Paula. And B and C. So they're not disappearing. They're not reacting. Each compound is going to be conserved. Yes. Why Team Kirby? Who is Kirby? Is that someone or? Oh, in a TV, what TV show?
It's called
Kirby. Look, I'm not that old, but oh, okay. Okay, action platform. I'm sorry. I'm sorry that I don't know Kirby. I was busy putting the lectures together. All right, so now I know. All right, so let's see who you guys got it. Most of you got it. So who would like to participate in telling us how to get to an answer? There's a group there. Duck, 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 goose. You guys have made any progress? That's okay. That's okay. Soup, team soup. Michael. Okay. Okay, at least kind of the methodology of getting the equations. Okay, what about you guys? Team Jupiter Snakes.
For our equations, we got the x1 plus x2 plus x3.
Yeah.
And focusing on the total mass. And
Got it.
You focus on the different compounds. So
Got it.
Compound A, you say
Mhm.
it's 2 kilograms going in.
Mhm.
So if you multiply the concentrations times the strain and add them up,
The mass fraction.
they
Yeah.
have to be
Yeah.
two.
Equal.
So we
Yep.
got like 0.04 times x1
Yes.
plus 0.54
Yes.
times x2 plus 0.2.
Yes. Correct. Thank you, Jupiter Snakes. So, you got the idea. And the idea is that the same way we have conserved the total mass of what's coming in and what's leaving by saying that 10 kilograms are coming in, that should be equal to x1 plus x2 plus x3. That's the mass that's distributed across the different separation columns. The same thing applies for each compound. Okay, so your colleague there said that, are there any reactions in these compounds? No, they're not changing, they're not disappearing. Compound A stays as compound A, compound B, and compound C, the same thing. So the mass of compound A, the mass flow rate of compound B, mass flow rate of compound C are also conserved. Okay, so we apply the same thing. We pick compound B, compound A, for example. So you get, for compound A, you get 0.04 x1. So that's the flow rate at station 1. 0.54 times x2 flow rate at station 2 plus 0.26 times x3 is equal to 0.2 times 10, right? That's what's coming in for A. And same thing for B. Now you could have chosen C, right? But then you will notice that when you create that set of equations, only 3 of them are unique. So you can use any 3 of those equations. Okay, the 4th equation is just going to be a copy of one of the other equations. Okay. It just so happened that I used AB, total flow rate plus A and B. Okay. So now the point of this is not to teach you separations, but just to show you that, hey, if you just assign symbols to things, you can derive systems of equations, okay, yourself. But the next step I want to make is to show you that this form is actually not very amenable to mathematical manipulation because it's annoying. Imagine having to write this form every time or having to write 1,000 of these equations. It's very annoying and not productive, okay? Not efficient. I don't like inefficient things, okay? So the first step I'm going to make in this is to combine the numbers for x1, so 1, 0.04, 0.93. They all multiply x1, right? So that's a vector with numbers 1, 0.04, 0.93, multiplying x1, right? So that's 1 times x1. And then 0.04 times x1, 0.93 times x1. Same thing for the second variable. You have 1, 0.54, 0.24 times x2. And same thing for the third, and equal 10, 2, and 6, right? So now, I hope that you can see that this is the same system of equations we had before. That's 1 times x1 plus 1 times x2 plus 1 times x3 equal 10. 0.04 times x1 plus 0.54 times x2 plus 0.26 times x3 equal 2, and so on. Okay, I want to take this one more step. My objective here is to get it into a form that is cleaner. Okay, so I'm going to take this one more step. These are just vectors multiplying these scalars x1, x2, x3. Now I want to combine x1, x2, x3 into a vector of their own. And then what happens is this. So if I write x1, x2, x3 as a column vector, this column vector, then these other vectors, 1 and 0.4, 0.93, they combine into a matrix. Prove it to yourself. You just did matrix vector multiplication in the exam. The first equation is 1 times x1 plus 1 times x2 plus 1 times x3 equal 10. The second equation is 0.04 times x1, right? Plus 0.54 times x2 plus 0.26 times x3 equal 2, and so on. So from now on, every time you see a matrix, think of this matrix as corresponding to a system of linear equations. Whatever that system comes from, okay, in this case came from separations, but it helps to have a meaning for things rather than just saying, oh, it's a matrix. What is a matrix? What is it representing? It's a coefficient matrix. Who cares? It represents a system of linear equations. It's solving something. It's trying to solve something, okay? But you see how we made it from what I called an ugly system of linear equations into, I think, a more elegant way to represent a system of linear equations. Because now, this matrix, I can take it and rip it apart and study it and understand its properties and make judgment calls about how to solve it, its eigenvalues, how fast can we solve it, is it solvable, et cetera, right? The system that we looked at before obfuscated that fact. So it hid that fact. We couldn't see this. Now there's an entire branch of mathematics that just talks about matrices and their properties, linear algebra. Okay. So now we call this matrix the coefficient matrix A. We typically use a bracket symbol around it, square brackets. We call this the solution vector. That's what you're trying to find the answer for. Okay. And we call this the right-hand side vector. So you will find that in my codes, I either use RHS for right-hand side or B, okay, whichever. So we started with separations. We wrote these three equations. Now we're doing matrix vector equal a vector. And now we're going to switch to a cleaner notation. Still, we're going to just talk about systems. When we talk about linear systems from now on, we're going to write them as AX equal B. Matrix A, coefficient matrix A, you're solving for the solution unknown vector X, which is a vector of unknowns, okay, equal to a right-hand side. Okay. So our objective is to find x, right? That's the objective of solving a linear system of equations. Okay, so this might seem a little bit silly, but I like to go through it just to show you that it's not as complicated as, or to just kind of reinforce some ideas that you might have learned before this class. So how do we find x? We have a matrix times x equal b. Let's take an analogy with a single equation. If you had a scalar, so 2x equal 3, ax equal b, then you would simply say x is equal b over a, right? So if this is 2x equals 3, you would say x equals 3 over 2. Okay, so why can't we do the same with this guy? Okay, wow, okay, I told you you're a tough bunch. We can't divide by a matrix, right? But what can we do with a matrix? Yes, and the word inverse, when applied to a scalar, it's 1 over, right? So the inverse of a matrix is actually the equivalent. It's as if you're dividing by that matrix, whatever that means. You cannot do division by a matrix. It's undefined. What do? You divide by each number in it. It just doesn't make sense. But if you take the inverse of the matrix, think of the inverse essentially, what is 2 to the power minus 1? It's 1 over 2, right? So A inverse, that's the equivalent of the operation of just solving for the unknown. Okay? It's just simply in a higher dimensional space. Okay? Okay, so now we have the matrix inverse, and now we can define the objective of linear solvers is to do one or more of the following. Either find the inverse of A, which is probably what you have learned in high school or other classes, right? Or find an approximation to the inverse of A. This is going to hint to iterative solvers. Or solve the system without explicitly computing the inverse. That's like Gaussian elimination, which is what you've learned, kind of solving it by hand. And the TDMA, the tridiagonal matrix algorithm, does that as well. Okay. But when you think about the theory of systems, linear systems of equations, or linear solvers, their objective is to take linear systems, either find the inverse, find an approximate for the inverse, or directly or approximately solve the system without finding the inverse. And we're going to learn about all of these options. Okay. Now we'll take a quick detour over here to actually show you how we're going to solve this using Python, because we need to figure out a way to find the inverse for simple systems like this: 3 equations, 3 unknowns, 10 equations, 10 unknowns. Just find the inverse and call it a day. Okay. We will learn, however, that as we go to much larger systems where you have millions of equations and millions of unknowns, don't compute the inverse. Probably take you a few years to compute an inverse. To store it is probably also, you got to buy Amazon Cloud or something. So we don't do that. But for simple systems, you compute the inverse. Okay, and we're going to show you how we do that in Python. You probably know, but that's okay. Then it'll be just a boring few minutes for you. The brute force solution is, the method you're probably familiar with, is to just directly find the inverse, multiply the inverse by the right-hand side, and that gives you the solution. Okay, so we're going to do this in Python, and I want you to grab linsolve activity 1.ipython notebook from the linear solvers module. Okay. So in Python, there are 2 ways to solve a system of equations directly. And those come from NumPy. There are other libraries that give you a linear solver, direct solvers. That's fine. We're going to employ numpy.linalgebra. So there's 2 functions. There's one called solve, which internally finds the inverse and solves the system of equations. And there's one called inverse, which is you find the inverse and then you take the inverse and multiply it by the right-hand side. Okay, so I've given you the code over here. You'll pull up your Jupyter notebooks, and I want you to kind of try to implement these codes. Okay, so that you can you get your hands, your muscles to practice. Okay. I'll do the same over here. And I think I might have this already open. Go to Jupyter. Okay. Go to Google Drive. This. Okay, so it's kind of hard to do it without. There you go. Okay, so I'm going to bring the slides to this. Do next to you over here. If I can find my cursor. All right. Okay, there you go. Okay. All right. So essentially just cannot type in the matrix, coefficient matrix. You'll notice that for very simple matrices like this, I just like to type in the matrix as a list of lists. So square brackets and then brackets, and just type it up the way it looks like. You know, you open the outer list on the outside, and then you put in the first list for the first row, second list for the second row, third list for the third row, and then define the right-hand side simply as a list. So call that a vector, and then declare your solution as solve A, comma B. So solve coefficient matrix with this right-hand side, and then print the solution. Okay, let's see what you've got. Most of you got it. Anyone struggling? Fairly easy. Okay, so let's see. You got 111 over here. You got 0.04, and then 0.54, and then 0.26, and then 0.93, 0.24, and 0.0, right? And for the right-hand side, we have 10, 2, and 6. Solve A, comma B. Now, if you're confused as to what the arguments of solve are, or what the arguments of any function are, you know, put your cursor right next to the parentheses over here. Okay, see my cursor? Put your cursor here and press Shift Tab. Shift Tab. So the button Shift and the button Tab on your keyboard. It's mind-blowing, right? And it gives you the signature of the function. Okay, solve A, comma B, solve a linear system, linear matrix equation, or system of linear equations. Now that's not enough. If you press it one more time, sorry, Shift Tab and then Shift Tab, it gives you the full documentation. So press it twice, Shift Tab, gives you the full documentation. Computes the exact solution X of the well-determined full rank linear matrix equation AX equal B. Okay, so that tells you what A is and what B is. So A is the matrix, coefficient matrix, B is the right-hand side. Okay, Okay, perfect. So now let's solve it. Boom, we got an answer. I hope that's the answer you got too. Okay. The other way, using the inverse, is simply you declare, I declare a variable called A inverse, and that's the inverse of A. Now, same thing for the documentation, shift tab, and it gives you the full documentation of the thing. Okay. So computes the inverse of a matrix. Given a square matrix A, return the matrix A inverse satisfying A dot A inverse is the identity. Okay. Now, you want to take that inverse and multiply it by the right-hand side vector. Okay. So that's a matrix vector multiplication. The way I like to do this is I type A inverse at B. I want to run this. Python does its magic, figures out the sizing and how it's going to do that product, and it does it correctly. Okay. That's the most direct brute force approach to solve a system of linear equations. You do this. When do you do this? You do it every time you're in doubt, when your system is small. You got like 5, 7, 8, 10 equations. You do this and move on with your life. And that's it. We can close the chapter and move on. But we're going to talk about other more complicated things because you're going to be facing much more complicated systems in your career, hopefully. Maybe not by the time you graduate, but one day in your life, you might face it. You say, I remember this crazy professor taught us about iterative solvers. So I'm going to pull up the slides. Hopefully you have them stored on your cloud or something. And so, and they might be worth something at that time. Okay. All right. Okay, if I can find my cursor. Okay. Now let's generalize. Any system of linear equations may be written in matrix form, where you have a coefficient matrix, you have a vector multiplying a vector of unknowns equal to a vector of right-hand sides. Each row in this matrix corresponds to one of the equations. Okay? The coefficients on this matrix, the coefficients of this row, correspond to the coefficients of the equation. So look at the first equation on the left, a11x1 plus a12x2 plus ... plus a1n(xn) equal b1. That's exactly what you have on the right. a11x1 plus a12x2, because that's the dot product of the row vector by the column vector, okay, equal to b1, and so on. Now, we have a nomenclature here where we have two indices, because the matrix is a two-dimensional beast, right? So it must have two indices. To find your way around it, you got to find what row you're at and what column you're at. That's one way to index it. So these indices that we have at the bottom, they designate your location in the matrix. So if I give you if I tell you aij is one of the coefficients in the matrix, that would indicate where that coefficient is located. And typically, the first index is the row, and the second index is the column. So A45 is the entry in row 4, column 5. Okay, A713 is the entry in row 7, column 13. A1n is the entry in row 1, column n. AMN is the entry in row m, column n. Okay. I never liked the aij notation because I and j, what the heck, right? I and j. Why didn't they call them ARC, a row column? So that's what I call them, ARC, because I deal with matrices every day in my life. Even my son now, my 4-year-old, knows about matrices. Okay, but I never got around to understanding this aij. It's annoying, so I call it ARC, a row column. All right. So if you like that, great. Okay. If you stick with aij, also great. But now you know kind of how to find your way around the matrix, okay, with this indexing notation. Okay. Now the last entry, AMN, is essentially telling you the size of this matrix. This matrix is an M by N matrix, M rows and N columns. Okay. Now let me ask you this. For this system, for this matrix, for this system to be well posed, what that means is, can we find an answer for this system? Can we find a solution? For it to be well posed, there should be a relation between the number of rows and the number of columns. Yes. Why? Okay, so let's translate that into something less abstract. When the matrix, Tata, those are all true statements, but I want to translate it into something that, you know, is more digestible. What does it mean when the matrix is square? When the number of, so when the matrix is square, number of rows equal numbers of columns. Yes.
You have the same number of variables.
Yes, you have as many equations as there are unknowns. So therefore you can solve it, right? And therefore that means you can find the inverse, right? So the abstraction to matrix form might obfuscate some intuitive facts, but always try to express an idea in something in words. Like, what does it mean when M and N are equal? It means we have as many equations as there are unknowns. What that means is that it's a well-posed system. We can solve it. We can find the solution. Okay. So what you all said is correct. Okay. I'm just trying to kind of phrase things in different words. The mathematical way is to say, yes, M needs to be equal to N. The matrix needs to be square. The matrix needs to be invertible. But also that means that same number of equations as there are unknowns. Okay. I have a couple more minutes and I'll finish off with this. There are many types of matrices that you will encounter in life as a human being. Okay. The most common type is when the matrix is full of entries everywhere. All the entries are non-zero, or most of them are non-zero. We call that a dense matrix. That's the one on the upper left. The next one is an upper triangular matrix where all entries below the main diagonal are zero. We call that upper triangular. Lower triangular is the opposite of that. All entries above the main diagonal are zero. A diagonal matrix is one where all entries are zero except on the main diagonal. Identity matrix is a diagonal matrix where all the entries are one. And a banded matrix is one where some diagonals are not zero, but everything else is zero. So banded, okay? Just bands. They might not be next to each other, but you might have one over here. You might have one over there. Okay, typically they are symmetric. Okay, but these are kind of the common types of matrices that you will encounter. And I will see you on next Tuesday. We'll continue our discussion on the topic. Thank you.